In this section, we're going to focus on index creation on our table structures within the HR database. Let's open our gedit window to discuss what we'll accomplish, and we'll discuss why indexes are important. So we're describing indexes and their value and creation syntax. So index creation syntax. Indexes allow data retrieval to operate much quicker than performing full page scans or row scans against a given table. Now, with small database structures similar to the ones we've defined, scanning the entire table structure occurs very quickly. But as your table structures grow, indexes become more valuable because they actually identify within the table structure on the physical disk where the data is located. So similar to the way indexes help locating certain topics within a book, indexes are typically located at the back of the book, and you can consult an index to identify specific areas within the book where you'll find certain topics. So indexes speed data retrieval by mapping interesting columns, for our intents and purposes, to file system locations. And we should note DBMSs by default perform entire row scans when attempting to find data. What this means is if you have a table with, let's say for example, one column, but this particular table, and we'll label it salaries, which we're going to define to illustrate our point, contains, let's say, 1 million possible values from 1 to 1 million for various salary ranges. Then that table contains 1 million rows. If there are no indexes defined on this fictitious, soon-to-be real salaries table, then when searching for values, let's say you want to return the salary 750,000, the database literally has to scan through each of the entries or each of the rows to find the magical row 750,000. Now, if it's a single column table, it may not take too long to find the row which contains 750,000 on a fast system, but with an index, it's much, much quicker. In fact, it's significantly faster, oftentimes orders of magnitude faster than performing full row scans. So wherever possible, try to identify columns within a table structure that can assist in retrieving data much, much quicker. You'll see that as multiple users connect to your DBMSs, and as your table structures grow and the contents of the table grows, you will need to define indexes on those columns that are of interest to help speed data retrieval. Now, MySQL supports using or lumping up to 16 columns into an index. So let's note that. And this is a current value. This is all subject to change, but 16 is the max. So MySQL 5.x supports 16 columns per MyISAM index. We're specifically mentioning the MyISAM storage engine, and we should specify in parentheses that this refers to the storage engine because this is the default storage engine that is used when you define tables within a MySQL environment, unless you specify a different storage engine such as InnoDB, CSV, Black Hole, example, and so forth. But if you don't specify a default or a different storage engine, the default MyISAM will be used. In the 5.x series, MyISAM is supported, ISAM is no longer supported. MyISAM is considered to be a fast, robust storage engine, but it is limited to 16 columns per index. So when you define indexes on a table, let's say for example your table contains 50 columns, but you must bear in mind that only 16 of them can be a part of the index. Now, another note is that oftentimes indexes end up being larger than the tables themselves. So you want to ensure that you provision enough storage for locating your indexes. So let's note that indexes often occupy more disk storage than the actual tables being indexed. But again, this is all to speed data retrieval, so you may be able to forfeit the storage in the event that you want to speed retrieval or for the sake of speeding retrieval. So it's a trade-off between storage and fast retrieval. You'll see the differences soon enough when we define our salaries table structure as a very simple but workable example. So some of the key things that we've noted thus far is that we're going to cover index creation, the syntax supported in MySQL, which matches the SQL standard. That's the international SQL standard. Indexes speed data retrieval by mapping interesting columns. Interesting columns are those placed into the index. It maps those columns to file system locations. As you know, tables are stored in file names, especially my ISAM tables are stored in file names with suffixes of .myd. Let's take a quick look at the file system. We'll SU in, and then we'll navigate once we've SU'd in to var lib MySQL. In var lib MySQL, you'll find the various directories for the MySQL databases, plus a PID file, log information, and so forth. We're not interested in the logging information just yet or error messages, but you do know that databases are stored within their own directories. Databases consist obviously of tables and indexes as the most common types of objects. So if you take, for example, the HR database that we've been working with, we'll navigate into that directory. You'll notice that there are files correlating to the tables that are defined, including employees, employees 2, as well as employees 3. But you do also notice that there are multiple names for, or multiple prefixes for the same file name. Employees 2 is represented 3 times, and as we've mentioned, each table structure is represented by an FRM file which describes the table, an MYD file which contains the data, and an MYI file which contains the index. Usually when an index is defined on a table, it's larger than the default index file, which is 1024 bytes. So in the case of the employees 3 table, this index doesn't appear to be used. It probably has no data, and that is the case because the MYD file is blank. The default size for the index on an x86 based system is 1024 bytes, whether or not the index is actually used or even defined. But by virtue of defining a table within MySQL, an index file is created, whether or not you define an index or a primary key or a unique index. So in other words, the MYI file is always there, and it serves as a container for index-related information. But you could feel free to create any index name, but they'll be mapped on the file system to the name of the table .myi. So if we created, for example, in the employees 3 table, an index that is called test index, a separate file called test index would not be created, but rather the test index would be stored within employees 3.myi. So those are just some things to keep in mind. But it's important to note the sizes again, default being 1024, whether or not indexes are actually defined. Super. So you know a little bit about how indexes are supported in MySQL, how many columns can be lumped into the index, and the fact that indexes could actually occupy or end up occupying more storage than the tables being indexed. Now let's take a look at what's actually set up within our MySQL instance by launching MySQL, followed by the prompt for the password. And once in, we are in the default none database. We don't have a default set, so let's show databases. You'll see MySQL along with HR. And since HR is our current database, let's use HR followed by show tables, and you'll see the employees, employees 2 and employees 3 tables. Let's execute a describe employees, and you'll see the columns that are defined, which constitute the employees table, and you'll also see that the ID column, which is an auto-incrementing column, is a primary key type column, which indicates that it is indexed. By default, when you define a field to be an auto-incremented field within a table, it gets indexed. So this means on the file system, there is space reserved for an index on the ID field in the MYI file, in this case for employees.myi. And as values are added to the employees table, that MYI file will grow. So in a separate window, let's SU in again, and then we'll navigate, once we've SU'd in, back to varlib MySQL just to drive the point home again. Let's navigate now into HR, and let's lsltr simply employees.star just to focus in on files related to the employees table. So here are the files that relate to the employees table, and we mentioned that there is an index defined. Let's just correlate it on the ID field by virtue of it being an auto-incremented field and being the primary key, which means that it's a unique index. This is just another way of saying a unique index to ensure that the values that are inserted are unique. But all of this information that you see represented for the ID column or the ID field, which is an indexed field, is represented on the file system by this MYI file that you see here, which is now twice the size of the default, which is 1024. So when you create a table, and whether or not it has an index, its default index file will be of 1024 bytes within an x86 base system. And once you begin to insert values into the table, the index file will grow. Now a simple select count star from this particular table, employees, will tell us how many values are there. Only one. We'd have to insert many values to cause the file to grow significantly, which we're going to do in the next section when we focus on defining a new table, which will contain simply one column followed by an index on that table, and to see some of the differences as we apply our queries in terms of performance or data retrieval. Super. So just to recap briefly, because we're going to get directly into creating indexes on our new table structure, here's how it works. We can create indexes on any table within the MySQL DBMS system. Indexes speed data retrieval by mapping the columns that you aggregate or lump or assign to the index to file system locations for the data, which means, once again, the index really references the locations in the employees.myd or in the tablename.myd file. This is the actual table data file. An index file really serves as a pointer or pointers to various locations in this tablename.myd file to speed retrieval, so that when you execute statements such as select against the table, the database checks to see, the database meaning the DBMS, checks to see whether or not any indexes are defined on the table. And if so, it consults the index first to see where the data can be found within the main table data file, which means that it's very important that we keep up to date our indexes so that our queries are always optimized. But again, there can be easily an order of magnitude or 10 times greater performance when an index is defined as opposed to when it is not defined. So for example, a query that may have taken 10 seconds in a very large table, let's say a table with 20 million records, let's say it took 10 seconds to return the row that we're interested in or rows that match our criteria, could easily take, instead of 10 seconds, 1 second when indexes are defined and defined properly, at the sacrifice, of course, of a little extra storage. But with today's cheap storage prices, it should be no big deal, and you should be able to allocate it as such. So one last note, indexes require extra storage, and you should consider storing indexes on a separate disk subsystem wherever possible. This means that if you're on a Windows system and you have, let's say, 2 drive letters, C and D, let's say your databases are on C, store your indexes on D. Or if you have drives D and E, store your databases on D and your indexes on E, or vice versa. And within a Unix type system such as Linux, try and mount your file systems in such a way that they map to physically separate disks. So if we execute a df, for example, notice that our primary file system location is the root, but we also have additional partitions. So ideally, you should separate your tables or your table data from your indexes, storing indexes, let's say, on one partition, SDB1, which in this case has 7 gigs available, and the primary table space data in a different partition such as SDA3, bearing in mind that indexes are easily likely to grow much larger than the actual table data. So that's a little bit about how indexes work. Next, let's create our new table and test accessing information from the table without indexes. We'll then define indexes or an index and then test retrieval to see how indexes increase data retrieval. Let's proceed with our study of indexes. So as you can tell, indexes are very important, although we've yet to actually prove it, but we will momentarily. So, you know that there are a maximum number of 16 columns per MyISAM index. That doesn't mean that that max applies to other storage engines supported by MySQL, but since MyISAM is the default, that is the case. Again, if you execute a show engines within MySQL, if you recall, you'll see the different storage engines that are supported by the current instance of MySQL on the system, with MyISAM being the default. This is the default engine, by the way, of MySQL, or used by MySQL as of version 3.23, which, as it says, provides great performance and so forth. But there are other types supported. Additionally, if you execute a show create table, for example, for the employees table, you'll see that the syntax includes the default storage engine, unbeknownst to you, the creator of the storage repository or the table. So by virtue of creating a table without even specifying an engine, MyISAM is the default engine. This means that if you intend to use a different storage engine for different reasons, let's say for scalability or for constraint support with primary and foreign keys, you could specify engine after the definition of the table by simply specifying engine followed by the name of the engine, which is returned by executing show space engines. Perhaps you'd want to run InnoDB instead of MyISAM if you need row-level locking, or maybe even CSV for outputting all of your data that's stored within the table structure to a comma-separated file for use within a spreadsheet. For example, that's a neat way of using MySQL, which provides a file that is readily usable and is parsable because it's CSV. So now it's time to create our structure, or to alter our environment to illustrate how indexes work. Let's show tables. Now in HR we have a base table called employees, and to show you copying table structures and the like, we created employees 2 and employees 3, but the base table and the base information still resides in the employees table. What we want to do is create, let's select star from employees just to see what's in there. What we want to do is create a dummy table called salaries. Oops, and we meant to specify from, and in salaries we're going to store possible ranges of salaries. So in our employees base table we have one record. We can update this later on, but this is not important. Let's say that eventually we intend to, for the sake of illustrating joins, which we will, alter the base employees table to include a column which includes a reference to the salaries table. That's what we're going to do at another point in time when we look at joins. We're going to reference the ID for the user. In this case, Tricia, her user ID is 1. We'll reference 1 to a key in a newly created table, let's say salaries. So for the sake of separating salary information in a separate table, we can perform joins to return the information that we're interested in, which means we'll need to alter employees to store the actual ID or the actual integer that's referenced over in the salaries table when looking up the salary for this particular employee. But more on that later on. So what we want to do is create a table called salaries, and initially it'll contain or be created with just one column called salary. So let's go ahead and create tables. So our task is to create a salaries, and we'll include it in single quotes, a salaries table with a salary column which will contain all the possible ranges or possible values for salary that any employee within our organization can earn. In order to do so, we'll execute a create table followed by the name salaries, which we can quote if we'd like, followed by open and close parentheses, and within the open and closed parentheses we'll specify one column salary. It'll be of type decimal, and we'll set a precision to be 11, 2, which means that it can store a total number of 11 characters, or in this case numeric values, which will allow us to create salaries as large as $9,999,000, 999, and so on. So let's copy this syntax and paste it into MySQL. And if we have create table privileges in this database, we'll be able to create the table. And now let's execute a show tables, and you'll see that we have a new table called salaries. Again, a show create table, and this is for the salaries table, will show how this particular table was created. Let's just find a recent command, show create table salaries, and just use it. And it shows that it was created with one column, which is set to decimal or a numeric holder, and its engine is MyISAM. But there are no indexes defined for this particular table, and we can prove that by executing a show index command. The show index command will tell us whether or not indexes are defined for a given column. If you want to see the indexes that are defined on the table, just execute it as follows. Show index from and the name of the table. In this case, salaries being the name of the table. If it returns an empty set, as it has in this case, then that means there are no indexes defined on the table. We can prove as such by doing a show index from employees, for example, and you'll see, let's execute that, that the employees table actually has an index defined, as we've mentioned, which is by virtue of defining a column as a primary key, which is a constraint, which is also an indexed constraint. So the employees table has an index on the column ID, and it is a key name or key type primary, and it's using B-tree as the algorithm, and its collation is default ascending, which means 1 first, 2 second, 3 after, and so on, whereas descending would be 3, 2, 1. Super. So show index from and the name of the table reveals indexes. A show index from salaries revealed no indexes. But we have our structure set up, and before we create an index on the salaries table, what we want to do is create a data set to be included into this table. Rather than using the database to create a data set, we'll return to the shell, that's the Linux shell, use the sequence command, which is excellent at just populating a file with sequential values up to any number that we specify, just given a little time. Then take that text file that's created and import it into the database. So let's do that. We'll need to create this file at least within the file system somewhere that the MySQL user can access, and we know that the MySQL user has full rights to var lib MySQL. So if we create the file outside of this file system space, we then need to move the file in here so that MySQL can read it, or alter our commands to specify a different location. So to make things as simple as possible, we'll create the file within var lib MySQL HR, because the file will be inserted using the MySQL import command into the salaries table into a column called salary. Super. So let's go ahead and set up this file. We'll use the sequence command. Now the sequence command will take two values, which really represents a range, so we could specify 1 to 100, for example, or we could just specify a number as high as 1,000,000 by specifying 1,000,000, or we could go as high as 10,000,000. In either case, this machine's quick, so the file will be created very quickly, and we'll send the output instead of to the screen, into a file called salary.txt. If you recall from our studies of MySQL import, if you have a file that has a name minus its extension that matches an existing column within a table, then MySQL will import directly to that column. So let's do a show tables again. We have a table called salaries. When we execute MySQL import, we're going to import into the HR database a file named salaries into the lone column that's in there. So we're going to call the file salaries.txt instead of salary.txt. So let's make it salaries.txt so that MySQL import will match the prefix salaries to the name of the table salaries. But we could instruct MySQL import to use a specific table. But this just makes it easy. So let's create this output file, and once finished, we'll see by executing an lsltrh salaries.txt that it's barely 7 megs. It's 6.6 megs, and if we were to tail it, you'll see that the last few values lead up to 1 million. And this is using notation. So we have 1 million rows, or 1 million values, 1 million possible salary values in this particular file. Now, of course, this may be a little extreme, since there is unlikely, even in the largest of organizations, for this sort of variation to be required. You'd simply key in the salary a person makes rather than going all out as we're doing here. But we're just illustrating how indexes work. Super. So we have salaries.txt. It's on the file system. Now we need to import this particular file into the salaries table. In order to do so, we'll use the MySQL import command. MySQL import followed by the prompt for the password, but we'll specify the password as ABC123. The default user is root, followed by the name of the database, which is the syntax that's required, and it's HR in this case, followed by the file that we'd like to import, salaries.txt. Now again, MySQL import will log in using this password and the default user root. It'll default the database to HR, and once it gets into the context of HR, it will attempt to match the file name prefix without the suffix to an existing table. So salaries should match salaries. And once within salaries, if we describe salaries, the MySQL command will simply import the text file into the lone column, which is why we defined it with one column to begin with. So let's go ahead and import it. And it should import very quickly. And also, as you know, MySQL returns the number of records. If there were any problems, any deletions, skipped, or warnings, in this case, no problems whatsoever. And there are no constraints on our column, so we could import this multiple times and duplicate the data, but we don't want to do that at this stage. So now that we've done that, the data is in our table, and if we were to execute a select count star against salary, or salaries that is, that's the name of the table, this will return the number of rows in salaries, and let's execute that with the from, which is why it returned 0, and you'll see that the proper result is reflected in the output of select count star. So this tells us that all 1 million records were inserted into the table structure. Now, obtaining a count from a table is always quicker than actually accessing the values stored within the table. So just keep that in mind. So don't be fooled by the fact that it took less than a full second to return the fact that there are 1 million rows. The count is considered metadata, and it's very easy or very quick for the DBMS to retrieve the count type information. But where it gets tricky is when we say return the row which contains 669,980, for example. So that would be an easy test for us. Let's go ahead and select star from. Now we could just as easily say select salary, but it's easier to specify star or asterisk than the actual name of the column, since there's a lone column. So select star from salaries will take a while to return all of the columns. This will take maybe a good 30 seconds or so to return all 1 million columns, and at the end of the output, the amount of time that the DBMS took to return all 1 million columns will be returned to us. You'll see that it actually took much less time than it's taking to display to the screen, because as we've mentioned in many editions of Linux CBT, writing to the screen is one of the slowest places to write. In this case, the DBMS thinks that it took less than a second to return all of the values stored in the 1 million rows. And it did. It returned it in less than 1 second, but it took our screen a good 30 seconds to display it to us. Now, less than 1 second may seem fast, but it really isn't if you consider the fact that we are the lone user connected to the server, which happens to be a pretty beefy server, which is dual processor based with hyper-threading, so it appears to be 4 processors with a lot of memory. So really, if you multiply our query times perhaps 100 concurrent users, returning 1 million rows of just decimal information in less than 1 second, or approximately 1 second, is really not fast. It should be considerably faster than this, and this is where indexes are going to help us. Now, before we exit and move on to the next section, which is where we turn on the index on the table, let's include a criteria here to increase the performance. Whenever you include criteria, SQL will, and whether it's MySQL, Microsoft SQL, Oracle, IBM, etc., any SQL will perform much quicker or much better than if you return all information from the table. So a full table scan is always going to take longer than select or criteria-based table scan. Let's include that where clause, and we'll say where salary is equal to 750,000. And you'll see that this query returns much quicker. 0.52, 0.53 seconds, and we could run it a few times. You'll see it'll alternate between 0.53, somewhere about half a second, which still seems fast, but you gotta consider if you have concurrent users, 100 concurrent users, 1,000 concurrent users, which MySQL can easily support on a properly tuned system, then half a second for such a simple query against a small table. This table contains 1 million rows, 1 column of just decimal related information, is way too long, which is why we want to apply our indexes. So next, we turn on the indexes and we see how performance is greatly increased. Now it's time to move on with actually creating the index on the table finally. Now again, you know, if we execute a show index from the name of the table, in this case salaries, it returns no indexes. Nothing has changed, and it still takes approximately half a second to return a unique value. So if we were to say we're salary instead of equal, like 750 for example, let's go with 700 or 75,000%, this will take even longer to return, 0.68 seconds, which returns values that are quite similar in nature. So this is still operating less than our expectations, so it's underperforming, and we want to increase the performance. How do we go about doing it? Well, there are no indexes defined, and the syntax for creating indexes is as follows. We're going to execute create index followed by the name of the index. Feel free to use the same table name or any name that you'd like. Let's go ahead and call it salaries for now, on the name of the table. In this case, it's salaries. So the syntax is create index, the name of the index, on the name of the table, followed by a list of columns up to 16 in between the parentheses. So this is where you specify your list of columns. So let's recap that syntax. To create indexes, you use notation such as the following: create index, index underscore name, on table underscore name, and in between parentheses, list of columns up to 16 for my ISAM storage engine. And this is a comma-separated list of columns. So that's the syntax. Let's go ahead and replicate it. Now for the salaries table, there exists only one column called salary. So we'll simply specify salary and nothing else. This will create an index called Salaries on the table Salaries based on the column Salary. Now the process of creating an index takes a little time. So let's go ahead and execute it, and you'll see that it takes a little bit to create it. It has to perform a full table scan, which means identifying this particular column throughout the entire DB, or throughout this entire table, that is. If you recall earlier when we executed a select star from Salaries, it took about 1 full second to return all 1 million results. Well, it takes about the same amount of time to construct the index on such a simple column. If you have more complex data or many more columns, then it'll take a longer time to create the index. The index now exists on the file system, and the time that, or the amount of time it took, the elapsed time, was returned as 5.23 seconds. What we want to do now is confirm what's occurred on the file system in terms of the growth in the index file. We're currently in varlib mysql hr, that's lsltr, and you'll see that salaries.myi is about 12 megabytes. If we execute lsltrh, and we'll focus in on just the salaries files, you'll see that the original salaries.txt file, which contains the 1 million records, is 6.6 megs. The description of the table hasn't changed, it's 8.4K. The salaries data file has changed from the original salaries table data file. It's now 6.7 megs, and it's approximately half the size of the index. So here's a classic example of the index being considerably larger than the table data file. The index is in the MYI file, and it's 12 megabytes. But guess what? When we now execute queries against the salaries table, extracting values from salary, the column, it'll occur much quicker. So let's note some of our previous runs. We executed a select star from salaries where salary like 75,000. We should copy this query and how long it took into memory and paste it into our text file. This particular query took approximately 0.68 seconds. Let's pick a most recent query where we selected a specific value such as a given salary, 750,000, and this took about 0.52 seconds. We're going to compare and contrast momentarily. This took approximately 0.52/0.53 seconds. We don't need the full word. So now we need to rerun these queries with indexes turned on, and we'll just copy the one that's in memory we'll use, so we don't need to copy it. Let's just make some space here and run it, and you'll see that the time wasn't even noted. Let's try it again, and we'll try it many times. With indexes turned on, it's considerably faster. This is much faster. This is many orders of magnitudes faster. In fact, this is 6 orders of magnitude, or roughly 5 to 6 orders of magnitude faster than had we had no index defined on the salaries table. So it does make a difference, and there is certainly a need for indexes, of course, at the sacrifice of disk storage, which is cheap by today's, or by any standard for that matter. So if you invest in storage, you can considerably appreciate the performance of your DBMS. Let's execute the other query, which took approximately 0.68 seconds, where we performed a specific query, or in fact this query has criteria which says like 75,000. Let's see if it takes close to 0.68 seconds or performs much quicker. And this query will run, and the initial run took 1.74 seconds, which isn't initially an improvement. Let's rerun it again. 1.74 seconds. Now without indexes, this is a particular query that ran much quicker. Now indexes don't benefit all queries, which is why we showed you the 2 examples. Here we're performing a like, and that like is taking a longer time to execute with indexes turned on, because the DB is actually consulting the index and then the table itself to scan for those values. But where you are more specific, searching for exact values, you'll find that there is no comparison. So there are trade-offs. The overwhelming majority of queries are going to execute faster within an indexed environment, but some queries, such as performing likes, will operate considerably slower. But generally, you'll perform direct queries, or you'll optimize your queries to be as precise as possible, so that your indexes actually pay off. Super. Now, as you know, the file has doubled in size, the index file, or in fact, the file has almost doubled in size that of the table data file. What if we were to go ahead and drop the index, just to show you the syntax, 1, and 2, to show you the performance degradation for optimized queries? The select star from salaries where salary like is not considered optimized. Select star from salaries where salary is equivalent to is an optimized query, because we're being specific. Whereas a search for matching values always takes a longer time. Now the syntax for dropping indexes is as follows. Drop index followed by index name on the name of a table. Table underscore name. This is the syntax. If we want to drop the index named salaries, we'll execute a drop index salaries on the table name salaries. And we'll follow that up with a query to see how much our performance has degraded. So now the index has been dropped. Let's confirm before following up with our query that the file system has been updated to reflect the new storage requirements for the salaries files. Notice that the index file has reverted to its default of 1K, which means the file is there, but there are no indexes defined or in use. So we've considerably reduced the storage requirements from a file system perspective, returning it from 12 megs to 1K. But now you'll see that optimized queries take considerably longer. So it's a trade-off between disk storage and performance. Let's go ahead and find the query in memory where we select a specific value, and notice that its results have returned to half a second, roughly. So we lose the performance that we gained when we dropped the index, which should be obvious. Let's go ahead and perform that like query, and you'll see that the like query performs considerably faster, and that's because the DBMS engine is dealing directly with the table. So as it performs the table scans, it's extracting the rows that contain values that are like what we're searching for, rather than consulting the index first and then the table. When indexes are turned on, they're consulted first, which means your queries should be optimized with indexes in mind. When indexes are turned on, they may add overhead when performing unoptimized queries when using like. Like is a flexible clause, but it comes at a performance price or a performance penalty. Super. So now if we wanted to turn the index back on to increase performance for optimized queries, we'd simply execute the create index command, and this time let's go ahead and create an index with a different name just to show you that it actually works. So this time we're going to create an index. We're going to call it test index sal on salaries using the same column, and it'll take approximately 5 seconds again to create the index. Let's exit this particular entry. By the way, I'm not sure if we've shown you, but if you've got, or you end up in a situation within the MySQL terminal monitor where you have a command that you want to erase or just instruct the shell to ignore, just use \C. Rather than using backspace to erase everything, \C followed by enter, and MySQL simply ignores what's typed in. Let's create this new index, and in fact, before creating the index, let's cancel what we're doing. We've already specified a semicolon, which is why the index is going to be created, so we'll let it run. The index is now there. What we wanted to show you was the fact that after dropping the index, a show index would reveal that no indexes were defined on the table. But now a show index from salaries will reveal that there is an index defined on the salaries table, and its name is test_index_sal, and it contains 1,000,000 records, and it's based on the column name salary, again with a limit up to 16 columns. Now when we execute an optimized query, you'll see that the performance increases are returned in less than a measurable amount of time. We're able to return specific information. So definitely implementing indexes provides significant advantages, of course at the trade-off of file system storage, because now our index file has returned to the 12 megs that we mentioned. Now we did mention again that if you use a different name for your index, as we did, let's do a show index from, the name of the index is test_index_cell, the index information still gets stored in a file called tablename.myi. So that's something to keep in mind. So indexes are definitely beneficial. The syntax is very straightforward. Simply create index, the name of the index on a given table, followed by open and close parentheses, and in between those parentheses you'll specify the columns up to 16 for the MyISAM storage engine. Once the index is in place, you'll notice that your file system has relinquished storage to the index, but at the trade-off of a significant performance increase in optimized queries, which means you want to think long and hard about the queries that you write. Use less likes, for example. Use less likes in your queries and you'll find that they operate much, much faster. So more equals and criteria that's as specific as possible so that you get more hits on the index than misses. And when you get more hits, then performance is significantly increased. That's a little bit about implementing indexes using the default storage engine within a MySQL framework. Again, the default storage engine is MyISAM. MyISAM supports up to 16 columns per index for a given table. And based on that, there are storage requirements which can easily double the size of your table data file. But if you have storage, create as many indexes as possible to increase the performance of the DB. Now as you scale your DBMS, you'll find that as more concurrent users, and concurrent users, by the way, doesn't only mean actual people, it means subjects such as applications. For example, web applications, front-end utility like utilities such as Microsoft's Access, or other front-end utilities such as a GUI tool for MySQL. There are different definitions for subjects, but subjects usually mean users of, which could be an application, a Perl script, a PHP script, or a physical user, an actual person executing all sorts of queries against your DBMS. So you won't notice the differences initially when one or two users connect, but as you scale, you'll see where indexes perform and pay off as a result. So that's a little bit about implementing indexes with the MyISAM storage engine.